Welcome to the Deep Dive, the show where we take a massive stack of sources and distill them down to the essential, mind-blowing insights just for you. Today, we are diving deep into a problem that costs global corporations, well, billions of dollars annually.
Billions. We're talking about trying to predict if consumers will actually buy the new product you've spent a fortune developing.
It's a huge gamble.
It is. It's the ultimate paradox. You need consumer sentiment, but traditional research is, messy, it's expensive, it's slow.
And it's biased, right?
Absolutely.
Right.
Think about it. When you fill out a survey, you might just be clicking buttons to get it done. That's called satisficing. Or you suffer from positivity bias, where you're just trying to be nice and you overrate things. The data ends up noisy.
Exactly. So you're making these multi-million-dollar decisions based on maybe a few hundred people who were maybe not even paying that much attention. Our mission today is to unpack a really revolutionary solution that's emerging from recent research.
And that is using large language models, LLMs, as sort of synthetic consumers.
Generating instant, cheap, and maybe even bias-free focus groups. This isn't just theory, right? We have some solid data here.
We do. The source material is very robust. It's a study that benchmarked this new method against 57 real-world product concept surveys.
And these are for what kind of products?
Personal care items. So think shampoo, lotion, things like that. And it's benchmarked against 9,300 genuine human responses, all using that standard 5-point Likert scale for purchase intent.
Okay, so the researchers had a clear goal. Can we get an LLM to give us data that looks and behaves like those thousands of humans?
That was the goal. But here's the core hurdle they hit right away.
The twist.
The twist. If you just ask an LLM a direct numerical question like, on a scale of 1 to 5, how likely are you to buy this?
Yeah.
It fails spectacularly. It gives you garbage data.
So the breakthrough isn't that we can use LLMs, but it's the revolutionary way they figured out how to ask them the question.
Precisely. And that breakthrough is called Semantic Similarity Rating, or SSR. We're going to walk you through how it works and show you why it achieved nearly human-level accuracy. We're talking reliability scores over 90%.
Incredible. Okay, let's start with that initial failure then. The first thing anyone would try. The researchers called it direct Likert rating, or DLR.
DLR is the obvious baseline, yeah. You give the model a persona, say a 30-year-old mother with a medium income. You show her a concept for a new anti-aging cream, and you just prompt it. Reply only with the number 1, 2, 3, 4, or 5.
Simple enough. So what happened? Did these synthetic consumers actually reflect what real people would say?
Not even close. It was a statistical nightmare.
Oh, wow.
When you force models like GPT-4o and Gem2F into that tiny numerical box, they just regress to the mean. They overwhelmingly chose 3, the safe, central, neither likely nor unlikely options.
And they never used the extremes, the 1 or the 5.
Almost never, which is the exact opposite of what real marketing data shows you.
Right. Real data is usually clustered at the positive end, around 4 and 5.
Yep.
You expect people to be either really into it or not at all.
Exactly. The LLM was just hedging its bets. So to quantify how badly the shape of that data was skewed, the researchers used a metric, let's call it a shape matching score.
And the scores were?
Abysmal. We're talking 0.26 for GPT-4o and 0.39 for Gem2F. When a perfect score is 1, anything near 0 basically means your synthetic panel's response pattern looks nothing like the human one.
But here's the part that's a bit tricky, and I want you to follow this.
Yeah.
Despite that horrible shape, the DLR method still got around 80% on the ranking correlation metric. So how could the distributions be total garbage, but the ranking was still okay-ish?
That 80% was driven more by coincidence and noise than real fidelity. It means that even while the LLMs were stuck mostly on 3, they would, occasionally shift to a 2 or a 4. And that was just enough to separate the really bad products from the slightly better ones. It was a rough ranking, but not something you'd bet your company on.
And I assume the researchers tried to fix this. Like maybe just nudge the model.
And they did. They tried using system prompts, basically telling it, hey, be more positive, use 4 and 5 more often.
And did that work?
It improved the shape matching score a little bit, but it completely destroyed the actual signal.
Yeah.
The ranking correlation just dropped like a stone. And that proved the core problem wasn't just the prompt. The LLM fundamentally struggles with being coerced into giving a single arbitrary number.
The moment you force it to do math, you lose the signal.
You lose the signal.
Okay, so if asking for a direct number is a total failure, this is where Semantic Similarity Rating, or SSR, just flips the script completely.
It does. The core realization was Stop asking the LLM to be a calculator.
And let it be a poet.
Exactly.
Right.
That's the aha moment. Don't ask for a number, ask for a natural language statement, and then use the model's incredible semantic power to translate that statement into a score distribution.
So you let the LLM do what it's best at, generating text.
You let it operate in its home turf.
Okay, let's walk through the 3 steps of SSR, because this is where the magic happens. Step 1 is textual elicitation.
Right. So the LLM gets the full demographic persona, the product concept, just like before. But instead of an integer, it replies with an unconstrained free text statement. It might say something like, the packaging looks sleek, the ingredients appeal to me, I would definitely consider buying this.
Okay, so you get this nice, rich sentence. Step 2 is embedding generation. How do you turn that sentence into a number?
You don't, not directly. You turn it into a high-dimensional embedding vector.
A vector.
Think of all possible opinions about a product existing on this huge, intricate map of meaning. When the LLM generates that text, we use another model, like OpenAI's text embedding 3 small, to convert their whole sentence into a single, precise coordinate on that map. It's like turning a paragraph into a latitude and longitude on the map of human sentiment.
That makes the next step, semantic mapping, much clearer. So now you have the LLM's thought as a point on this map. What's next?
We use predefined reference statements as our anchors. We set 5 fixed points on that same map, 1 for each Likert score from 1 to 5.
So the 5 anchor might be a statement like, I would definitely buy this right now.
Precisely. And then we measure the distance using cosine similarity between the LLM's generated point and those 5 anchor points.
So you're not forcing a hard 4 or a 5. If the LLM's response is semantically really close to the 4 anchor, but also a little bit close to the 5 anchor, the system actually captures that ambiguity.
Yes, that's the key. The similarity measurement creates a probability mass function, a PMF, over the 5-point scale. It's a distribution of likelihood. The LLM's response might register as, say, a 60% probability of being a 4F and a 40% probability of being a 5.
Which is how you capture that nuance and uncertainty that exists in real human sentiment, instead of forcing a clean but potentially wrong single number.
That's it. It's far more elegant than another method they tested called follow-up Likert rating, or FLR.
Where second LLM acted as a Likert expert to assign the score, right?
Right. And FLR was better than the direct method, DLR, but SSR was vastly superior. And it's because it doesn't try to assign a number. It uses the semantic space to assign a distribution.
Which better matches the complex statistical nature of real human responses.
It successfully leverages the LLM's deep understanding of language without forcing it to do a cognitive task it's not really designed for.
Okay, that makes perfect sense conceptually. Now the big question,
Yeah.
did this complex 3-step process actually deliver the results?
It was astonishing. When they applied SSR, the synthetic consumer panel just suddenly started replicating human behavior with incredible accuracy.
So let's go back to that shape matching score, the metric that was in the gutter before.
The 0.26 and 0.39 scores, yeah. How did SSR fix that problem of the LLMs just clustering around 3?
Yeah.
Well, the shape matching score for GPT-4 immediately jumped to 0.88.
Wow.
For Gem 2, it hit 0.88. I mean, that is phenomenal. It means the synthetic responses now had the same realistic, positively skewed distribution that the real human data showed.
The synthetic data didn't just look random, it looked human.
It looked human, but the real bottom line for any company isn't how pretty the data distribution looks.
It's, can you trust it to rank your products from best to worst? We're talking metric 2. Relative concept appeal, the ranking correlation.
This is the headline figure. SSR attained correlation values of 90.6% for Gem 2F.
90%.
And 90.2% for GPT-4o.
Okay, let's just pause on that for a second, because a 90% correlation is huge. The researchers had already established a reliability ceiling for the human data itself, right?
They had. They simulated a test-retest scenario by splitting the real human cohort in half, and that gives you the maximum attainable correlation. It represents how consistent the human data can possibly be.
And the synthetic panels approach that absolute ceiling.
That's the implication here. Running a synthetic panel with SSR is now nearly as reliable as commissioning a whole new, very expensive human cohort to run the exact same survey.
This validates synthetic consumers for mission-critical, quantitative decision-making.
It does, but here's where it gets really interesting.
Oh.
The synthetic panels actually proved to be more aggressive in their feedback. The mean purchase intents from the LLMs were more spread out than the human data.
More spread out how?
They were more negative about the truly unattractive products than their human counterparts were.
So that human positivity bias we mentioned at the start.
The synthetic consumers seem to suffer from it less, which means they provide a stronger, more discriminative signal.
So for a company that's trying to filter out the duds, the really rough concepts early on,
The synthetic panel might actually be a superior tool because it's less polite.
I could see a product manager loving that. Data that's not only reliable, but actively cuts through the noise of human agreeableness. So we've established the SSR method is incredibly accurate. But I want to circle back to the persona. One might assume the product description is all that matters, but the research suggests that giving the LLM a specific demographic persona is absolutely essential.
It might be the most important finding outside of the SSR method itself. They ran an experiment where they used the perfect SSR method but deliberately removed all the demographic conditioning.
So no age, no income, just a blank slate LLM.
Blank slate. And what happened was counterintuitive. The distribution shape was almost perfect.
Light.
The shape matching score hit 0.91. The average purchase intent across all 57 concepts was a perfect replication of the human average, 4.0. Visually, statistically, it looked perfect.
So the LLM, without any context, knew how to sound like a generic human statistically. But what about the ranking?
That's where it all fell apart. That perfect-looking data was worthless for decision-making. The ranking correlation attainment tanked. It dropped all the way down to only 50%.
50%, so basically a coin flip.
Right. The models without demographic context just became generally positive. They gave a nice-looking response distribution, but completely failed at separating the good concepts from the bad ones.
So the conclusion here is that the persona isn't just window dressing. It forces the LLM to process the product concept in a meaningful context.
Exactly. If you don't tell it who it is, it can't tell you why it likes or dislikes something.
And when it is conditioned correctly.
It successfully mirrored complex, nuanced human segmentation. It replicated what's called concave age behavior lower purchase intent for the youngest cohorts, who can't afford it, and the oldest cohorts, who are set in their ways.
Interesting.
It even mirrored income sensitivity, where purchase intent only jumps for the highest income levels.
And this brings us to what you call the qualitative goldmine, the actual text output from the SSR process.
Yes. In a traditional survey, you ask for open-ended feedback. You might get, it's good, or I don't like it.
If you're lucky.
If you're lucky. But the synthetic consumers, as a byproduct of this process, provided feedback that was so much richer and deeper. They gave detailed rationales, raising specific, actionable concerns, all in character.
Can you give us an example of that kind of depth?
Sure. Instead of a human just saying, sounds expensive, the synthetic consumer might say something like, the price point is concerning given the generic packaging design. It seems a bit too high-end for my needs, and I'm not sure the microbiome claim is worth the extra cost.
That is so much more useful. That helps product developers understand why their concept scored a 3 instead of a 4.
Exactly. And finally, just to put a pin in this, we should note the benchmark against traditional methods.
Right. How does this stack up against standard machine learning?
The researchers trained a supervised ML model, a light GBM classifier, on all the product and demographic data. This conventional approach, which needed training data, could only achieve a correlation of 65%.
And the LLMs with the zero-shot SSR method hit 90%.
Without any training data. It just underscores the massive inherent advantage of LLMs. Their pre-trained, deep semantic understanding is simply better at modeling human judgment than statistical classifiers trained on limited survey data.
Okay, so let's wrap this up. The key takeaways for you. First and foremost, Semantic Similarity Rating, SSR, is the game changer here.
It eliminates the core weaknesses of using LLMs for this kind of research. The failure of direct numerical input and those resulting unrealistic data distributions.
And it delivers on all fronts. You get high quantitative accuracy, that 90% reliability figure that approaches the human consistency ceiling.
Well, at the same time, you're generating this rich, interpretable, qualitative feedback that companies desperately need to actually improve their concepts.
And the best part is the efficiency. This is a plug-and-play, zero-shot solution.
No fine-tuning, no training on consumer responses. That means it's scalable, it's instant, and it's incredibly inexpensive compared to deploying huge human panels. This could really disrupt market research.
But as with any powerful new tech, there have to be boundaries.
Of course. And the success of this study was rooted firmly in the personal care product domain. And there's a reason for that.
Why was that such fertile ground?
Because LLMs have been exposed to vast amounts of consumer discussions, forums, reviews, e-commerce sentiment about shampoos, lotions, and soaps during their training, they already know what a 30-year-old mother thinks about anti-aging creams.
Which leaves us with the final provocative thought, something for you to mull over. Can this framework be reliably extended to entirely new, niche, or highly technical product domains where the LLM's background knowledge might be sparse or even non-existent?
Right. If you ask a synthetic panel about consumer interest in, I don't know, a new type of quantum computing hardware or a highly specialized industrial lubricant, will the LLM just make up preferences based on generic human traits, or will it admit ignorance? The validity of these synthetic consumers, it seems, is fundamentally bounded by the knowledge domain of the model itself.
A truly fascinating line of research, and one that forces us to constantly check the boundaries of what these models truly know.
Indeed. We'll catch you on the next deep dive.